Okay, so let's get started. Oh, by the way, there is the project proposal that is due today. So if you haven't done that, yeah, you can turn it in on Canvas. And of course, the instructions are on Canvas as well. And once those are all turned in, I will give you some feedback on your proposal. If I have any suggestions or anything, and I might ask you to sort of adapt it a little bit if I have some questions or something like that. But yeah, let me know if you have questions. You could stay after class or come to office hours. Yeah, if you want to do two related topics, that's fine as well. Just as long as it's not too long, I guess. That would be the only issue. Yeah, cool. So let's start. So we are now starting on chapter 4. And this is going to be on eigenvalues, eigenvectors. So did I say chapter 4? I meant chapter 5. We're starting on chapter 5. Okay. So yeah, this first section, we're going to talk about what is an eigenvector and an eigenvalue. Okay. So let's just start off with a definition. So this is going to be for square matrices only. So an eigenvector of an n by n matrix is going to be, we'll say n by n matrix A is a non-zero vector. So the zero vector cannot be an eigenvector. That's important. So non-zero vector X such that A times X is equal to lambda X. Okay, so this is the definition of what it means to be an eigenvector. And what this is saying right here is that for this particular vector, multiplying by A on the left is the same as just multiplying by a scalar. So here lambda is a real number, right? So in this particular direction, multiplication by A is just scaling the vector. And this doesn't happen in every direction. It's for particular directions. And we can only have so many of these special directions for one n by n matrix, right?
So multiplying the vector by that matrix is just the same thing as scaling that vector by some scalar?
Yes,
And
exactly.
that's an eigenvector. Okay.
That's what an eigenvector is, yes. Right. So, and then this scalar that we get, this lambda, is what we call an eigenvalue. So okay. Okay. And so there is a correspondence between these eigenvalues and eigenvectors. So when we talk about an eigenvector, we could say that it has an associated eigenvalue, lambda, whatever that may be. And then if we're talking about a particular eigenvalue, we could say it has an associated eigenvector x, right? So there's this correspondence between the two. Okay. Right, and just to just emphasize this again, an eigenvector is non-zero by definition. And this is because if we look at a times 0 equals lambda times 0, this would be from our definition of eigenvector, then this is true for all lambda. So the question is, what is the eigenvalue in this case? It's not really well defined.
It can be anything.
Yeah, it could be anything. Yeah, so it's not really what we would consider an eigenvector, right? Okay, so let's look at some examples. Right. So consider the 2 by 2 matrix. A, that is 2, 2, minus 4, 8. And the following vectors. So we're just going to check R, V, and W eigenvectors of A. Right? And to check this, we're just going to compute, A times V. So if we do that, we get 2 plus 2 for the first entry, and then minus 4 plus 8, which is 4, right? And that is equal to 4 times V, right? Because our V is just 1, 1. So we do get that A times V is equal to some scalar times V. So V is an eigenvector. And the eigenvalue is, or with eigenvalue, lambda equals 4. Right. Okay, and let's check the same thing for W. So here we get A times 2, 1. And this will give us 6. And then negative 8 plus 8, so 0. Right? And then there's no constant that we could multiply this by to get W, right? So this is not equal to some constant times W. So W is not an eigenvector. Okay, so those are some examples. One thing to point out is that even though 0 cannot be an eigenvector, the constant 0 can be an eigenvalue. Even though the 0 vector cannot be an eigenvector. Okay, so let's look at an example of that. If we have A is equal to 2, 6, and we have minus 3, 1, then if you look at A times V, this is the following, which gives you minus 3 plus 3, so 0. and minus 6 plus 6, which is also 0, which is equal to the constant 0 times the vector v, right? Or maybe I'll just write it this way. 0 times v, right?
So V here is an eigenvector here.
Yeah, so v is an eigenvector with eigenvalue 0. So notice the eigenvector itself is still not 0. It's not the 0 vector, but the eigenvalue is 0. Okay. So it's good to try to picture what's going on here. So if V is an eigenvector of A, what that means graphically is that A times V and, A times V and V, yeah, V are collinear with the origin. Okay, sorry. Okay, so let's look at a picture. So say we're in R2, we have our origin right here, right? And we have some vector v. Now, if A times v is equal to lambda v, then we have that A times v will be some scalar multiple of v, right? So it'll be somewhere along this line through v, meaning that it is collinear. So if we were to draw a line through all of them, the origin v and A times v, those are all collinear, right? And for instance, if you have another vector w, we'll say is not an eigenvector, then A times w will end up being not collinear with the origin in w. So it's not just a scaling of that vector, it sends it to something on a different line, right? Collinear with the origin. Right. So I guess I'll get rid of this. Collinear with the origin means the line through the origin and V passes through A times V. Is that? Okay, cool. Yep. Okay, so this is how to sort of picture what's going on with an eigenvector, right? Yeah, I think there's also a nice picture in the textbook. So I guess another way of thinking about this is as a transformation, right? So if you have t of x is equal to a times x, right? So this associated linear transformation in the directions that are eigenvectors. So say we had v and w. Maybe I'll put it on the axis. Yeah. what this is saying is that in these particular directions, you get only stretching. I'm trying to draw this in a way that looks right. So T of V is just a stretching of these directions. In the other directions, you get more, so it'll be linear combinations of these, which will give you sort of distortion. So you could see, like, these are the special directions where you just get this like stretching like this in this direction and that one. And then other ways, it's not just stretching, right? For instance, this vector here. Okay, anyways. Okay, so if we're given an eigenvalue of a matrix, then we can figure out what the corresponding eigenvector will be. And so say we're given that 2 is an eigenvalue of the 2 by 2 matrix. This is 1, 3, 2, minus 4, right? Okay. And then we want to figure out what are the corresponding eigenvectors. There could be more than one, right? Okay. So if V is an eigenvector, then we have this equation. So that would mean that A times V is equal to lambda times V. Oh, where lambda is 2, so let's just put in 2 there, right? So just multiplying this out, we can figure out, so we'll say this is the vector with entries v1 and v2, then 2 times v is 2v1, 2v2. And then on the left-hand side, we can just write this out. So v1 plus 2v2 for the first entry and 3v1 minus 4v2 for the second one. So we just actually have an equation, right? So this tells us that if V is an eigenvector, then we get V1 plus 2V2 equals 2V1, and 3V1 minus 4V2 equals 2V2. And then we can just move these guys to the other side. So negative V1 plus 2V2. And this one is 3V1 minus 6V2. Both are equal to 0. Okay. So the second equation is actually a constant multiple of the first equation. So what we get is that in general, V1 should be equal to 2V2. And this is, for instance, satisfied if V is equal to 2, 1, right?
Do you put like a number, or not a number, do you put like V2 in front to indicate that you want to multiply the vector by whatever value of V2 you have?
Right, you could do that, but yeah. So yeah, you could do it that way. And then you could see that, I guess we could write it this way, is equal to 2, 1.
Yeah.
Right, yeah. So in fact, anything in the span of 2, 1 is also an eigenvector, right? But so in particular, this 2, 1 is an eigenvector.
Do you have to say anything about how the 0 vector can't be? Or is that implied?
Yeah, no, you don't have to say, yeah. I guess, right, you wouldn't want to write down an eigenvector. If you're looking for an eigenvector, you don't want to say it's 0, but actually I'll talk about that later, but yeah, so okay, we'll get to
I guess
that.
I meant, like, do you need to clarify for all v2 not equal to 0? But
Right. Yeah, I mean, I guess that, yeah, it's good to do that, yeah. Okay, cool. Right, yeah. Okay, so okay. You guys can hear me? Okay, cool. Let's see. So there's a little bit more efficient of a way to solve this. So if lambda is an eigenvalue, then we know that means that A times V equals lambda times V, right? And we can rewrite lambda times V as, well, we can rewrite, yeah, this as lambda times 1, 0, 0, 1 times V, right? We just insert the identity matrix in there, which doesn't change anything, right? And then we can move it to the other side and we get 1 times V, and we get the 0 vector on the right-hand side now. And we have, this is a matrix, right? If we insert lambda into here, or we could just leave it this way, this is also a 2 by 2 matrix, right? And we can factor that V out on the right-hand side, right? So here, I'm just gonna rewrite this as just I. So lambda times I, and we factored out V, right? Okay, so what this means is that if V is an eigenvector, then you get that it satisfies this equation, right? And this is just some matrix, right? So it's saying that if V is an eigenvector, or let me put it this way. Or V is an eigenvector corresponding to lambda if V is in the null space of A minus lambda I. Right? Because V will be a solution of this homogeneous equation, meaning that it will be in the null space. This is sort of ignoring the fact that the null space always contains the 0 vector, and we don't refer to the 0 vector as an eigenvector, but assuming that this is not just equal to the 0 vector, then we say that V is an eigenvector. Okay. And so the nice thing about formulating it this way is that we already know that the null space is a subspace, right? And so we get something called the eigenspace, which will also be a subspace. Okay, so the eigenspace of A corresponding to lambda is the null space of this guy A minus lambda I. And this eigenspace is denoted E sub lambda. Okay, that is the eigenspace corresponding to lambda. Okay. Okay, then if lambda is not an eigenvalue, or sorry, if lambda is an eigenvalue, then E sub lambda is a subspace spanned by one or more vectors right? So this is saying that if you do have that lambda is an eigenvalue, the corresponding eigenspace will be at least dimension 1. You'll have at least one eigenvector in one direction, right? Which actually gives you infinitely many eigenvectors because everything in that span is also an eigenvector. And the eigenspace being a null space is a subspace of R. Of Rn when A is an n by n matrix, right? Okay. And so finding the eigenspace or finding a basis for the eigenspace is going to be the same process as we've been doing for finding a basis for the null space, right? So the only thing different is the setup. So let's do an example. So say we have the matrix A, which is 1, 3, 0, -1, -1, 2. Okay. And we're given that lambda equals 2 is an eigenvalue. And we want to find a basis for the corresponding eigenspace E sub 2. Right? So what we want to do is look at A minus 2i, right? That's that A minus lambda I, where lambda equals 2. And we're going to look for the null space of this matrix. So first let's compute it. So this will be the matrix A minus 2 times the identity matrix. So it will just be 2, 0, 0, 0, 2, 0, 0, 0, 2. Right. So if we compute this, we get 1, 1, minus 1. We get 1, another 1, minus 1. And the last row is all zeros. So we have a duplicate of, so the second row is exactly equal to the first row, so it will disappear when we row reduced. And we have the following matrix, which means that the null space of A minus 2I is equal to the span of, here we would have, oh, let me actually write this out more in more detail. So we get from this, x1 is equal to negative x2 plus x3, and both x2 and x3 are free. So x will be equal to x2 times negative 1, 1, 0 plus x3 times 1, 0, 1. Right? Okay. So this will be equal to the span of those two vectors. Is everybody good with that part? Okay, cool. All right, so like I said, it's just a matter of using the same techniques that we've been doing for finding the basis for the null space. We just have to compute what it is that we're looking for here. So A minus 2I. Right. So one thing to know about these eigenvectors and eigenvalues, so why do we care about them? They can help us understand the behavior of a linear transformation. So knowing the eigenvectors and eigenvalues of A can help us understand the behavior of these linear transformations, right? So let's look at an example. So for instance, if T is the linear transformation that is the reflection over the line y equals minus x, so in R2. So the line y equals minus x is right here. And so this is saying that this just tells you this is the linear transformation that gives you the reflection over this line, right? So we could compute the actual matrix that corresponds to this transformation, but we don't need to do that to figure out what the eigenvectors and eigenvalues are for this, right? Because it's a pretty simple transformation, right? We can just picture where each vector would end up being mapped to under this transformation. So if you have a vector v, we know that it just gets reflected in this line. So its image will be, T of v will be over here, right? And remember that a vector is an eigenvector if v and T of v are collinear with the origin, right? So this vector that I drew here is not collinear with T of v and the origin. V, T of v and the origin are not collinear. So this is not an eigenvector that I've drawn. But if it were the vector, I'll draw it in a different color, that is perpendicular to this line. So it'd be, say, if we took, let's say x was 1, 1, right? That would be exactly perpendicular to this line y equals x, and its reflection over x or over y equals x would be in the exact opposite direction, right? This would be T of X over here. And since these are collinear, this is an eigenvector, right? So let's write this out. If X is equal to 1, 1, T of X is collinear with X and the origin, or we'll just say the 0 vector, right? Since T of X is just going to be, when we flip it over that line, it'll be -1, -1, right?
When you say the origin, are you referring to it as a point or just as the x-axis?
I'm referring to the point right here.
Okay, the point of, so I guess that could be, so this is just two-dimensional though. We're not,
Yeah. Yes.
this like
Just
in the
these.
z-axis perspective? Okay.
Yeah, this is not a z. This is supposed to be the line y equals -x. Right. Okay, and this is R2. Okay, so notice that we have that this x turns into x, which is 1, 1, turns into -1, -1. So x is going to be an eigenvector with eigenvalue -1. Actually, let me write this on the next page. X is an eigenvector with eigenvalue -1. Okay, does that part make sense so far? Okay. Let's see. Okay, so that is in one direction. The other direction that is sort of special is if you are exactly on the line y equals x, right? So on the line y equals x, so say if we're focusing on this direction here, I'll just call this W. This direction, when you flip over the line, since it exactly lies on the line, it actually doesn't change at all, right? So reflection over the line for a vector that lies on the line is just the identity, it doesn't change it. So if W is, for instance, to make it simple, we can just take the vector -1, 1, right? That lies on the line y equals x, or y equals -x. Then T of W actually just sends it to itself, right? And so this is an eigenvector with eigenvalue 1 because it didn't change it at all. Oh, sorry. Eigenvector with eigenvalue lambda equals 1. Okay. So what we get is that the eigenvalues are equals 1 and lambda 2 equals -1, just to differentiate them. And E lambda 1, which is the eigenspace for lambda equals 1, is the span of, what was it, 1, 1? No, -1, 1. And then E lambda 2, which is the eigenspace for -1, is the span of 1, 1. And so these are the eigenspaces.
Are these the two special eigenspaces you were talking about before? Like, are these worth remembering?
Which one? What was I talking about before?
I don't know. I'm sorry. I got confused. I thought you said something about these being like special or having special properties.
So the eigenspaces are the eigenvectors tell you the special directions in which the linear transformation only like stretches each vector.
Okay. Sorry. I'm having a hard time holding all of it in my head. I have like a hard time taking in all the information.
Right, yeah. Okay. Well, right. Try to take in as much as you can, and then you can always go back over it later and try to understand a little better.
Thank you.
Yeah. So this is another way of thinking about eigenvectors and eigenvalues, right? Okay. So let's see how we're doing on time. Okay, cool. Yeah. So we have the following theorem regarding eigenvectors. And I think we will not prove this, but it is proven in the book, so you can reference that. So eigenvectors corresponding to distinct eigenvalues are going to be linearly independent. This. Right, so that's just like the plain way of saying that, but if you want to be more specific, this means that if you have a collection of eigenvectors of a particular matrix, maybe I'll put this way, of a matrix A, and these correspond to eigenvalues lambda 1 up to lambda k, which are all distinct, so none of them are equal. Then this collection of eigenvectors is linearly independent. Okay. And so, like I said, these will be, this is proven in the textbook, but we're gonna skip over the proof for this. Okay. So now let's think about what we've gone over and how it relates to what we've been doing in this class, right? So if we have that lambda is an eigenvalue of A, this happens if and only if this equation, so A minus lambda I times V equals 0, has a non-trivial solution. Right? If it had a trivial solution, then we get that our supposed eigenvector is just the 0 vector, which is not allowed, right? Okay, so this is true if the null space of A minus lambda I is not just equal to the 0 vector. Right? Okay. And then also, as we discussed before, finding a basis for the eigenspace, the lambda eigenspace of A means finding a basis for the null space of A minus lambda I. And so we've had some practice with this, so we should know that we do this by solving the homogeneous equation. So solving A minus lambda I times B equals 0. Okay. And so just like with the null space, the dimension of the eigenspace is going to be the number of free variables in the equation, the homogeneous equation, right? Which is the number of non-pivot columns of A minus lambda I. Okay, and then finally, this equation, A minus lambda I times V equals 0, this has a non-trivial solution, meaning that it corresponds to an eigenvalue. This has a non-trivial solution if and only if A minus lambda I is not invertible, right? So we're using parts of the invertible matrix theorem right now. And this is true if and only if the determinant of A minus lambda I is equal to 0, right? So remember that if the determinant is equal to 0, you get that the matrix is not invertible. Okay. And so this last formulation is actually what we will use to find eigenvalues of A. So up to this point, we've been given that, lambda is an eigenvalue of A, and then we go about finding the eigenspace. But this will give us a way to actually figure out what the eigenvalues of A actually are, right? So this is how we will figure out the eigenvalues of A. Or maybe this is better, it's better to say find. Yeah. Okay, which is what we are about to talk about now. And so this is moving into section 5.2. And this is called, or so this is about the characteristic equation. Okay, so the idea here.
Oh, so if you can you scroll back up?
Oh yeah, sure.
So does this use the fact that it has a non-trivial solution to say that it's not invertible? Is this
Yeah.
part of like the invertible matrix theorem?
Yeah, exactly. Yeah. Yeah, so non-trivial solution. So it's sort of the opposite like statements for each of the equivalent conditions in the invertible matrix theorem. So remember, everything that we listed was equivalent to a matrix being invertible. And so now we're talking about this not being invertible. So that means that this has a non-trivial solution, that the determinant is equal to 0, and all of those sort of like opposite statements that we had. Okay, great. So using this idea, the idea here is that lambda is an eigenvalue of A if and only if the determinant of A minus lambda I is equal to 0. So we are going to find eigenvalues by solving this equation. Yeah. Right, so this will give us an equation and we just go about solving it. Okay, and so it'll be a little bit easier to see this by looking at an example. So let's look at a relatively simple 2x2 example. Right, so say we have the matrix 1, 5, 6, 2, and we want to find the eigenvalues of this matrix. So we will look at A minus lambda I. Let's compute that first. So this will give us lambda times I is just lambda 0, 0, lambda, like that, right? And then when we combine these two matrices, we get 1 minus lambda in that entry and 2 minus lambda down there. Right, so this is that matrix A minus lambda I for a general lambda, which we don't know yet. And the determinant of that, this is just a 2x2 matrix, so we can compute the determinant fairly easily. So this is this guy minus 30, and we can just multiply this out and we will get a polynomial in lambda, right? So this is 2 minus 2 lambda minus lambda plus lambda squared minus 30. Minus 28, right? So this is going to be what we're looking for are roots of this equation, right? We want to set this equal to 0 and solve it. And so in this case, this is just a matter of factoring, right? So we can factor this into -7 and +4, right? And so that means that the roots of this equation, which are our eigenvalues, are -4 and 7.
Should we like brush up on our skills for solving polynomials, because it's been a bit since I've had a class?
Yeah, maybe a little bit. Yeah, it would be a good idea. So I will go over an example for a degree 3 polynomial, which is a bit harder than degree 2. For degree 2, you can you can always use the quadratic formula, so that's an option. And then you can also factor, right? So yeah, if you need practice with that, it'd be a good idea to brush up, but it shouldn't be too difficult, right? So these are our eigenvalues. So there are two things that came up in this example that we'll have sort of names for. The first is this determinant of a minus lambda I gave us a polynomial in lambda, right? And this is what we will call the characteristic polynomial, right? So this will always give us a polynomial in lambda. And this equation, so we had this was equal to 0. So this right here, the equation part is what we call the characteristic equation. Okay, cool. So let's see. Right. Okay, so we have our eigenvalues, and just to finish off, even though we've technically finished the problem, we can practice finding the eigenspaces as well, since it's good practice. So if we're looking for the associated eigenspaces, right, so we have two eigenvalues, so we'll have to do two separate parts for this. So if lambda is equal to -4, then a minus lambda I is actually a plus 4i, which is, so our matrix is 1, 5, 6, 2 plus 4, 0, 0, 4, which is 5, 5, 6, 6, right, which reduces to 1, 1, 0, 0. So your general solution here would be t times 1 minus 1. And the eigenspace is then just the span of this one vector. So span of 1 minus 1. And then we can do the same thing for lambda equals 7. So a minus 7i is going to be,
Pardon me.
yeah.
Oh, never mind. I understand what you did with the negative. Okay.
Oh, okay. Yeah, I guess I kind of flipped it around. But, right. Okay, so here we get -6, 5, and 6, -5, right? Which row reduces to just, squeeze this in here, negative, well, I could write it this way, 6, -5, 0, 0, right?
Yeah.
And then, yeah, okay, cool. And then our general solution would be of the form t times 6, 5. So our eigenspace for 7 is the span of this vector, 6, 5. Okay, so just to recap, the determinant of a minus lambda I gives us a polynomial in lambda. This is the characteristic polynomial. Right. When we set it equal to 0, we get an equation. This is the characteristic equation. And the solutions of the characteristic equation are the eigenvalues of A. And sometimes for this characteristic polynomial, we'll use the notation P of lambda since it is a polynomial in lambda, right? So just so you're aware. Okay, so let's look at another example so we get more used to this. We'll do something a little bit more complicated. So this will be a 3x3 matrix. So this 3x3 matrix here, right? So we are going to compute the determinant of A minus lambda I, right? So if we look at A minus lambda I, that will be, we'll just get negative lambda in each of the diagonal entries, right? So those were all zeros. When we subtract lambda I, we'll get negative lambda for each of those. And the other entries stay the same. 0, 0, 1/2 minus lambda. And we just want to take the determinant of this guy. Right? So this is a 3x3 determinant. This first column has a 0 in it, so I'm going to choose that to expand it. Right? And we would get negative lambda times minus lambda 0, 1/2 minus lambda. And then we get negative 1/2 times the determinant of this guy. Okay, so we get negative lambda times lambda squared minus 1/2, and this will be negative 6 lambda minus 4. Okay, so here we do get a degree 3 polynomial, right? So this is plus 3 lambda plus 2. Okay, so we want to solve this equation. So this guy equals 0. And we could go about doing this. Well, let's just remind ourselves of the rational root theorem if you have forgotten it. So like it says in the title, this will only tell you the rational roots of this polynomial, but a lot of the time we do have rational roots when we have these like the types of problems that we have in like textbooks and these types of things. It's nice to have rational roots, so it's good to check for them, right? Okay, so this says that lambda will be equal to plus or minus all of the factors of 2, well, there's only 2 of them, 1 and 2, divided by all of the factors of the, so this is the last coefficient over the first coefficient, right? And the first coefficient is just -1. So in fact, the only possibilities that we get are plus or minus 1 and plus or minus 2. Okay. Right. So
me.
yeah, go ahead.
This is you said it's the reversible root theorem?
Oh, rational root theorem.
Rational root theorem. Sorry, my brain broke. I haven't heard of this. If I did, it was a while ago.
I think this like these are like all the possible rational roots.
Yeah, all the possible rational roots, and they are not all going to be roots of this polynomial, right?
Okay.
Okay.
So does it come from the potential? I'll just look it up.
Okay, that's probably good. Okay, so the way that we can test whether these possible roots are actual roots of our polynomial, the easiest way is just to plug them in, right? If they make the polynomial 0, then it's a root. If it doesn't make the polynomial 0, it's not a root, right? So let's go ahead and start plugging in. So starting with lambda equals 1, we get, if we plug this in, -1 plus, this is confusing. We get -1 plus 3 plus 2. So this is not equal to 0. So that's not a root, right? Let's check some of the other ones. So -1, if we plug that in, we get -1, so we get +1, -3 plus 2. So this one actually is equal to 0, right? Okay, so that means that lambda plus 1 is a factor of this polynomial, right? So if we go ahead and divide by lambda plus 1, then we'll get a quadratic, which is a lot easier to solve, right? So let's go ahead and do that. So if we take lambda cubed plus 3 lambda plus 2 and divide by lambda plus 1, I should leave a little room for this. So we're doing just the long division.
Long
right?
division.
Yeah, long division.
Okay.
Yeah. So we would need negative lambda squared to get negative lambda cubed. And then we would get a negative lambda and subtract. And that would give us lambda squared plus 3 lambda. And then we would need a plus lambda to get lambda squared. And then we would distribute to get plus lambda and subtract again. And that will give us 2 lambda, pull down the 2, and we get 2. And so we shouldn't get a remainder if it is a factor, so it's good that we get 0 here. And then now we have that negative lambda cubed plus 3 lambda plus 2 is equal to this factor lambda plus 1 times, now we have negative lambda plus 2. Okay. Which we can factor, right? If that negative bothers you, we can just pull it out. So we get lambda squared minus lambda minus 2, right? And then we should get here, got a minus 2, so we need minus 2 and plus 1, right? You guys agree?
Yeah.
Okay, cool. Right, so we have lambda plus 1 squared times lambda minus 2. Okay, so we have two solutions. One is a double root, right? So we get lambda equals 2, whereas, yeah, 2 and minus 1, where minus 1 is a double root. So the number, so this has multiplicity 2, this root minus 1. So this is what we refer to as the algebraic multiplicity. This is the number of times that lambda appears as a root. Is called its algebraic multiplicity. So this is in contrast with what we will call the geometric multiplicity, which we'll get to in a second. But first, let's look at the eigenspaces, right? Okay, so we can go about computing the eigenspaces. So there will be two of them since we have two eigenvalues. Let's start with 2. So for lambda equals 2, we are looking at a minus 2i. And remember that our matrix is 0, 6, 8, 1 half, 0, 0, 0, 1 half, 0. So this will be minus 2, 6, 8, 1 half, minus 2, 0, 0, 1 half, minus 2. Okay.
Oh, wait.
And
Oh, did you row behind you?
oh, minus 2i, sorry.
Yeah, is this
Minus,
mine?
I forgot to write this part. Minus 2, 0.
Okay.
Yeah.
That makes no.
Okay, there we go. So we have this matrix and we want to row reduce it in order to find the null space, right? So let's go ahead and sort of normalize these constants across the board. So I'll multiply the first row by negative 1 half so that I get a 1. So that'll give me minus 3, minus 4. And then I can multiply the next two rows by 2 to get rid of those fractions, right? So I would get 1, minus 4, 0, and 0, 1, minus 4. Okay, and then I can take row 2 minus row 1 to get rid of that 1 in the first column. So 0, we get minus 4 minus negative 3, so that would be 1, and then 4, right?
Wait, I see.
Is that right?
Wait, you replace row 2 with row 2 minus row, so it'll be -1, yeah.
Negative 1, yeah. Okay, there we go. And 0, 1, minus 4.
Oh,
And
okay.
then the third row is a constant multiple of the second row, so it will go
It's
away.
rows.
And we have 0. I'll make this 1 minus 4. And that is in row echelon form. And if we want reduced row echelon form, we just have one more step where we get rid of this minus 3. So we can take row 1 plus 3 times row 2. And that will give us 1, 0, and then negative 12 minus 4, so negative 16. Okay, so from this, we can see that x1 is equal to 16 times x3. x2 is equal to 4 times x3, and x3 is free. So in general, our solution looks like 16, 4, 1, right? And so that means that our eigenspace for 2 is the span of this vector, 16, 4, 1. Okay, so that was the first eigenvalue. The second eigenvalue was -1, right? So we're looking for the eigenspace of this guy, right? So we're looking at a plus I because lambda is equal to -1. If we compute that, we get 1, 6, 8, 1 half, 1, 0, 0, 1 half, 1. Okay. And then again, we're going to want to row reduce. So again, I'm going to multiply the bottom two rows by 2 to get rid of the fractions. So we don't have to deal with those. So 1, 2, 0, 0, 1. 2. And then I'll take row 2 minus row 1, which would be 0, -4, -8. Yeah. And then 0, 1, 2. Okay, and in fact, row 2, well, row 3 is a multiple of row 2, so it'll go away. And I can divide row 2 by -4, so I get 1, 2, 0, 0, 0. And then I can take row 1 minus 6 times row 2, which would be 6 times 2, so -4. Yep, 0, 1, 2, 0, 0, 0. Okay, there we go. That is reduced row echelon form for this guy, and we have that x1 equals 4 times x3, x2 equals -2 times x3. And that means that an x3 is free, so x is equal to x3 times 4 minus 2, 1. And the eigenspace is the span of this one vector minus, 4 minus 2, 1. Okay, so we have our two eigenspaces, right? Each a span of one vector. So one thing to note is that the dimension of this eigenspace for -1 was 1, right? It's a span of one vector, even though its multiplicity as its algebraic multiplicity was 2, right? So even though it was a double root of the characteristic polynomial. Right? But there is actually a relationship between the number of times that the root appears in the characteristic polynomial and the dimension of the eigenspace. And it is this. So in general, the dimension of the eigenspace for lambda will be less than or equal to the multiplicity, the algebraic multiplicity. So it will be less than or equal to m, where m is the algebraic multiplicity of lambda, right? Okay, so for example, if your characteristic polynomial, once you factored it, looked like lambda minus 1 times lambda minus 2 squared times lambda minus 3 cubed, right? So you have 3 eigenvalues, 1, 2, and 3. Then you know for sure that the dimension of the eigenspace for 1, your lambda equals 1, is equal to 1, because it will be at least 1, right? You have at least one eigenvector corresponding to that eigenvalue. You know that for sure. So the dimension has to be less than or equal to 1, it has to be greater than or equal to 1, so it is equal to 1. The dimension of the eigenspace corresponding to 2, it could be 1 or 2. But you don't know for sure until you actually go about solving for the eigenspace, right? So again, because the multiplicity on 2 is 2 in the characteristic polynomial. And then the dimension of E3 is 1, 2, or 3 because the multiplicity is 3 there. So it has to be something greater than 1 and less than 3, or less than or equal to 3. Right? Okay. And then whatever the dimension of the actual eigenspace, or whatever the dimension ends up being of the eigenspace, is what we call the geometric multiplicity, right? So the dimension E sub lambda is called the geometric multiplicity of lambda, right? So it's related to like how large the eigenspace actually ends up being, whereas the algebraic multiplicity comes straight from the polynomial, right? Okay, we won't get into this too much. I just thought I would mention it since it's good to know. So it's nice to know these things so you can double check that your answer makes sense, right? Okay, so how are we doing on time? Oh, we're out of time. Okay, right, we are out of time, right?
Yeah.
Okay. So we will continue with this section next time and also move on to 5.3. No, we won't. We'll do the exam next time. Sorry. We'll continue with this on next Monday. But the exam will be in class on Thursday. So maybe I'll write that down.
And so in the study guide for the exam, I guess would you suggest that we go through the suggested problems and those will be somewhat similar to what will be on the exam?
Yes, they'll be similar.
Okay. Thank you.
Yeah, no problem.
Is there a workshop today?
Yeah, there should be.
There's a problem session today.
Yeah,
Problem set? I don't remember what it's called. The thing.
Yeah.
about workshops.
something like that. Yeah.
All right. Thank you.
Okay. Yeah, no problem.
Did you write the questions for this problem session?
Yeah, I have not yet